Hi everybody. Today's lesson is on doing an estimation of the population mean, and the first thing that we need to talk about is what's called students' t-distribution. If you want a really interesting and kind of funny story about how companies keep their stuff secret, go and read about the t-distribution, because it was actually discovered by someone who worked for Guinness Beer in Ireland. It's a really cool story. So when we deal with the t-distribution, we want to suppose that it's from a simple random sample of size n, and we're going to assume this population is normally distributed if it's less than 30. If it's greater than 30, then we know from the central limit theorem that the distribution, whether it is a t-distribution or an left skewed, right skewed distribution, it goes normal. So this is usually for sample sizes that are less than 30, but if they're less than 30, they have to follow a normal distribution. And if they're greater than 30, they don't typically have to follow the normal distribution, but we use a t-distribution because we're going to put the sample standard deviation in place of the population standard deviation. Remember, the population is kind of that thing that sits out there. We don't usually know that kind of data because we can't get to every member of a population usually. So we're usually stuck with using the sample standard deviation, and therefore we're going to use a t-distribution. All right. Now, when we talked about standard deviation before, the reason that we had to have n minus 1 in the denominator was because of what's called degrees of freedom. And for a t-distribution, the degrees of freedom is n minus 1. So this t-distribution looks a lot like a normal distribution. And the t-distribution, the degrees of freedom shape it. It is still mound shaped, but the size or the width of the t-distribution is based on that degrees of freedom. The curve is symmetric around 0, just like the standard normal curve. Same as the standard normal curve, the total area under the curve is 1. And the area in the tails, the normal distribution kind of flattens out and gets closer to 0, but the area in the tails of a t-distribution, even though it flattens out, there's usually more area in the tails than there is in a standard normal distribution. And as the sample size increases, the t-distribution starts to go normal. All right, so that is the kind of distribution that we're going to be dealing with today. So, what about estimating a population mean? Remember that the sample mean estimates the population mean, and again, just notation wise, we've got x bar, which is the sample mean, and the population mean is mu. Alright, so we want to do a point estimate for example. We have the 2016 Chevrolet Equinox has the following fuel efficiency miles in miles per gallon for a sample of 14 vehicles, and we want to find a point estimate. So the first thing that we want to do is we want to find x bar, which we remember is add them all up and divide by how many there are. And I'm just going to let the calculator do that for me. Just give me a second to put all this data in here. Alright, so we've got 19.6, 25.8, 22.1, 26.6, 25.3, 21.4, 19.0, 21.2, 25.9, 20.3, 18.5, 21.0, 19.1, and 17.9. And I want to do one variable statistics and we get an X bar of 21.69. Alright, so the point estimate for the population fuel efficiency is excuse me, 21.69 miles per gallon. Okay. Now, just like we had critical values for the standard normal distribution, we have critical values for the T distribution. Now, I will send you a copy of the T distribution chart. It is in each one of the problems that requires it on the My Math Lab homework. Again, what you want to make sure of is that the table that you look at is, you look at the picture so that you can make sure that the question that is being asked, you can find it with the table. Alright, and I just want you to notice that this table is actually different from the table that is given to you for the standard normal distribution. The table here is given so that you're given that the area in the right tail is the value that's in the chart. Alright, so let's look and see how that's read in the problem. It says, find the T value such that the area in the right tail is 0.01 with 17 degrees of freedom. Alright, again, what does that look like? We know that we have 0.01 in the right tail, and we have degrees of freedom equal to 17. Alright, so we know that it is 0.01, and degrees of freedom is over here. And I want you to make sure that you can kind of know that this is degrees of freedom, because degrees of freedom are not given to you usually in the problem. The sample size is usually given to you. So make sure you always know what's given and how to find degrees of freedom if you're given the sample size. Alright, and again, degrees of freedom in this problem are 17, so I'm going to go to 0.01. And I'm going to go down to 17. So the value that we would use is 2.567. So this T alpha over 2 value is 2.567. Alright, just to do another one of those, we have find the T value such that the area in the left tail is 0.025. Okay, so that's not exactly what was given before. We know that the area in the left tail is 0.025, and we have 8 degrees of freedom. Okay, again, this chart is like the standard normal curve in that it is symmetric about 0. So this area to the left is the same as if I was given the area to the right. But we know that a number that is left of 0 is negative. So whatever my answer is, I'm going to make it negative. So I've got 8 degrees of freedom with 0.025. And I'm going to just go down and I get 2.306. So it's going to be negative 2.306, and that is the value that I would use for my T alpha over 2, my critical value. Alright, now the way this is set up, because we're going to do a confidence interval, is we want to find the critical T value that corresponds to 98% confidence. Remember that when we do this, we're going to set it up 0 in the middle, and we know that we're 98% confident that that mean is going to be somewhere in between there, okay? Which means we're leaving ourselves 2% error, and that is our alpha, okay? So if I split 2% evenly, that means there's going to be 0.01 in each tail. So now I have an area in the right tail, and we know there are 22 degrees of freedom and 0.01. So 22 degrees of freedom and 0.01 would be 2.508. So my T alpha over 2 value would be 2.508. And that would be the critical value that we'd use for our confidence interval. Okay, so what is a T interval? A T distribution, you have to have a certain set of things that happen. We know that the data comes from a simple random sample or a randomized experiment. We know that the sample size is small relative to the population, which means that we know our sample size is less than 5% of the population, and that the data comes from a normally distributed distribution if it's usually less than 30, and if it's greater than 30, it doesn't necessarily have to be normally distributed. Okay, so here is the interval. The lower bound is our sample mean minus our critical value times the sample standard deviation over the square root of n to the sample mean plus our critical value times the sample standard deviation divided by the square root of n. Just remember that this is kind of the same thing as the proportion that we dealt with in the last problem. This is just, in the last problem it was a z instead of a t. So it's still kind of the same formula. Alright, and remember you have n minus 1 degrees of freedom. So there is the interval. Alright, so let's do an example. Alright, a simple random sample is drawn from a population that is normally distributed. The sample mean is found to be 18.3. So we know that x bar is equal to 18.3, and we know that our standard deviation is found to be 4.1. So our S is equal to 4.1. So we want to construct a 90% confidence interval about the mean if the sample size is n is equal to 19. So if n is equal to 19, that tells me that my degrees of freedom is equal to n minus 1. So it's going to be 19 minus 1, which would be 18. Alright, so that's going to help me find that critical value. Alright, so let's go do that. We know that we're going to do a 90% confidence interval. So if we are 90% confident, we know we have 90% in the middle, which leaves me with 10% for error, which means that in each tail we would have 0.05. So I'm going to look up 0.05 with degrees of freedom 18. 0.05 with degrees of freedom 18, and we get 1.734. So that is going to be my T alpha over 2 value, 1.734. So now my lower bound is x bar minus my T alpha over 2 times my standard deviation over the square root of n, and that's going to be 18.3 minus our 1.734 times 4.1 divided by the square root of 19. Guys, remember that this is going to be n. That's not your degrees of freedom. I usually have people that will make a mistake by putting the 18 degrees of freedom for the n. So don't make that mistake. Alright, so if I just put that in the calculator, I've got 18.3 minus 1.734 times the standard deviation 4.1, 4.1 divided by the square root of our n, which is 19, and that gives me 16.67. And we know that our upper bound is just a plus sign instead of a minus sign in the middle. So we have x bar plus t alpha over 2 times our standard deviation over square root n. So that's going to be our 18.3 plus 1.734 times 4.1 over square root of 19. And Michelle's going to snag that from up above and just change that to a plus sign. And I get 19.93. So, again, if we're going to interpret that, that would say we are 90% confident that the true mean of the population is between 16.67 and 19.93. Alright, so that's for a 90% confidence interval. Let's do for a 95% confidence interval. Alright, so we want to construct a 95% confidence interval about the mean if the sample size is 8. Alright, so again, we're going to come over here. We want to do a 95% confidence interval, and we know that our n is equal to 8, which means that my degrees of freedom is equal to n minus 1, so 8 minus 1 is equal to 7. Alright, we know that leaves me with 5% error split evenly would be 0.025 in each tail. So that means I'm going to look up 0.025 with degrees of freedom 7. So 0.025 degrees of freedom 7 gives me a t-value of 2.365. So my critical value is 2.365. So I'm going to go do my confidence interval with the mean minus my 2.365 times the standard deviation 4.1 over the square root of 8, and that's going to give me 4.1 minus 2.365 times 4.1 divided by the square root of 8, and that gives me 0.67. And if we just change that subtraction sign to an addition sign, we're going to have 4.1 plus 2.365 times this 4.1 over the square root of 8. Let me snag that. Go change that to a plus sign. And I get 7.53. Alright, so one more of these and then we'll be finished with doing a sample. Alright, so we want to construct a 99% confidence interval about the mean if the sample size is 35, which means that our degrees of freedom would be 35 minus 1, or 34. Looking at my t-chart or t-graph, we know that we want to be 99% confident, which means we're leaving ourselves 1% error. And if you divide 0.01 divided by 2, you're going to get 0.005. So that tells me that I've got 0.005 in each tail. So that is my area, 0.005 with degrees of freedom 34. 0.005 degrees of freedom 34 gives me 2.728. So that is my T alpha over 2 value, 2.728. Lower bound, 4.1. Y'all let me do this without doing the 18.3. These should be 18.3. I was wondering why I was getting so many messed up numbers. Let me go back and do those right quick. The mean is 18.3. 18.3 minus 2.365 times 4.1 divided by the square root of 8. So we get 14.87. And if I change that to a plus sign, I get 21.73. Now, if I come down here and try to do it correctly the first time, I get 18.3 minus 2.728 times our standard deviation over our square root of n. And that's going to give me 18.3 minus 2.728 times 4.1 divided by the square root of 8. And that gives me 14.35. And change that to a plus sign. And we've got the upper bound, which is going to be 18.3 plus 2.728 times 4.1 divided by the square root of 8. And that gives me 22.25. Alright, and that is how you find the confidence interval for a population mean using a t-distribution. I'll do a real-world example in the next video. Thanks, guys.